Good evening, everyone. My name is Kevin, and in this assignment, our group have choose the free space Optic performance for our assignment title. So there will be two circuit that we have created. One is the single channel one, and then in this single channel, we have used the pseudo random bit sequence, NRZ path generator, MAC random modulator, and CW random for our transmitter. And in the middle, we have the FSO channel and the optical gain. For the receiver, we have the photodetector pin, low pass laser filter, and DVR analyzer. So for the first part, I'll be presenting to Roshini. Okay.
Okay, so now we have set the beam to 0.5 millirad. Okay, so the results. Okay, so for the beam divergence of 0.5 millirad, it has a better Q factor of 10.0953 and a lower BER of 2.8823 e to negative 24. Okay, for the beam divergence of 0.6 millirad, this shows the 0.6 millirad for the beam divergence, and here we can say that the Q factor of 7.11344 and a minimum BER value of 5.64028 e negative 13. This weakens the system since the Q factor falls and the BER rises compared to the 0.5 beam divergence. Now we will see the 0.7 millirad. Here now, I have changed the beam divergence to 0.7 millirad, and we can see it has a Q factor of 5.29012 and a minimum BER value of 6.0891 e to the power negative 8. Okay, so this is the weakest among the two since it has the lowest Q factor and the greatest BER values when compared to the other two. Thank you.
Okay, so this is our second circuit, which is the multiplexing circuit. So in the transmitter side, we have four sets of the pseudo random bit sequence, NRZ, path generator, MAC render, and the CW laser. And then we attach it to the WDM mux 4x1. And after that, we will have the optical gain and the FSO channel. After that, we attach it to the WDM DMUX 1.1x4. For the receiver side, we have the photodetector pin, low pass laser filter, and the 3R generator. So for the first presenter of this circuit, I'll leave it to Dinan.
Okay, my part is the based on the result when the divergent value is 0.3 mrad. So as we can see here, there's a consists of 4 channel of BER analyzer. So when the result came out, the first BER result is going to be for the first channel is going to be the Q factor is 8.41 835, And then for the second BER analyzer is going to be 8.14674. And then for the third one is going to be 8.32282. And then and then for the final one is going to be 8.13648. So this is the 4 result for the BER analyzer when using 0.3 mRad divergent. So now I would like to give the opportunity to Kausi to present the divergent for 0.4.
Hi, my name is Kaushana Prabhakaran. So now we are going to look at the value of 0.6 mRad on the beam divergence. So we'll be getting 4 outputs here. And yeah. So we can see the first output is the XQ vector is 8.37. Second one is 8.06. Third one is 8.31 and the fourth one is 8.00. So compared to the output showed explained by Lini just now for 0.3, we can see that the Q factor has already fallen. So when the BER value increased, the Q factor falls. So that's all from me. Then 0.5 will be explained by that.
My name is Narendra Amidashan. Now I will explain about the difference after we change the value in FSO channel, the beam divergence into 0.5. So as you see here, so for the BER analyzer, so the first one, so the maximum Q factor will be 8.26885. Then the BER analyzer 1 will be the maximum Q factor will be 7.90688. BER analyzer 2 will be 8.23703, the maximum Q factor. And then the BER analyzer 3 will be 7.955, the maximum Q factor. So the conclusion we can observe from the simulation is that the changing the beam divergence parameter affects the BER and Q factor values. As the beam divergence values increase, the entire system performance weakens as the BER value increases and the Q factor falls.